Can hear you now.
Thank you.
You can introduce yourself if you want, Ray. We can take this moment.
Okay. Thanks, Kate. Uh, Sorry about that. Um, the only thing I really wanted to say is I wanted to reiterate what Kate said about the importance of all of you, the operators. Uh, in so many aspects of what we're trying to do, we absolutely depend on you. Without you, we can't do our job. And that's especially true with any kind of unusual treatment, or in this case, the cyanotoxin. So I just want to say how appreciative we all are of your participation in this. And as you know, I am always available to you, whether it be a cyanotoxin issue or any of your treatment issues. So uh, feel free to call me anytime. Thank you.
Thanks, Ray.
And Kate, I just wanna tag along to that. What Ray just
Mhm.
said is so true. And if you can't get a hold of Ray, feel free to call me. And then if I can't help, I'll figure out when Ray is available, or there's an engineer on staff, or Kate is on staff. So definitely don't hesitate to reach out.
Yeah, and for everybody, you could actually call Silly first. That would be fine too.
You're welcome. You're welcome to.
All right. I'm just going to say a note here for folks that are joining the recording late. We missed a couple of slides, so I'm picking up about 4 slides into this presentation. um, I'm going to carry on with the rest of this little section though. So as I said, we've yet to identify a scientific consensus on why cyanobacteria produce cyanotoxins in the first place, and that can make it really challenging for us to be able to predict when blooms might become toxic and when we can expect to see cyanotoxins, in our drinking water. However, there are two primary schools of thought or hypotheses as to why cyanobacteria are producing toxins in the first place. And they tend to fall into these two groups of being that they might provide the cells producing them with some sort of competitive advantage against other cells or other types of algae or phytoplankton, or the other is that they could provide defense mechanisms either against competing phytoplankton or against zooplankton that might feed upon them. So there's been some research that shows that microcystins particularly can be used to help cyanobacteria in nutrient scavenging, so they can bind nitrogen to the toxins, and those might be able to be held intracellularly and broken down later on and used to help the cyanobacteria producing them access nitrogen when it might be limiting. And then other ideas is that they could provide them from oxidative stress. So if you imagine on a lake in the summer, you're sitting at the top of the water column, there's a lot of intense light coming in, and the UV radiation can break down cells and cause oxidative stress. And there's been some research that's shown that toxic cyanobacteria can outcompete non-toxic strains of cyanobacteria in the presence of this high light conditions. And then alternatively, we can see that cyanobacteria can potentially have some protection from grazing if they can produce toxins. So some zooplankton can be selective about feeding what types of algae or phytoplankton they want to eat. And oftentimes they can sense that the toxins are present and they will choose not to feed upon cyanobacteria that can produce toxins. And I also put this last bullet called allelopathy, which is essentially cyanobacteria that can produce microcystins are sometimes thought to be able to inhibit the growth or success of other phytoplankton species due to this chemical, due to the microcystin chemical being produced. So as I said before, our overall lack of understanding on cyanotoxins makes it critical that we have systems in place here to be able to monitor when blooms might become toxic and when the public will be at the greatest risk for toxin exposure in drinking water. So that leads us into the cyanobacteria monitoring program. So this program is a voluntary, no-cost program to analyze microcystins in surface water sources. The program is open to all public water systems that are sourced by lakes, ponds, and reservoirs in Vermont. And we request that participating water systems are going to collect samples from raw and finished water weekly from the week of June 7th into November 8th. Or not June, sorry, July 7th into November 8th. And then the overall aim of the program is to further understand, thank you for letting them in. The overall aim of the program is to further understand the statewide risks of cyanotoxins in drinking water sources with an overarching goal of protecting public health. So last year we had a total of 7 microcystin detections, with only a few of those being confirmed samples from the following week. And these were all detected across 2 water systems from Lake Champlain and one inland lake sample. And then we didn't have any detections in any of our finished water samples. In Lake Champlain, microcystins were primarily detected in the northeast arm, which is the more eutrophic, shallow side of the lake where blooms tend to be the strongest and longest in duration. And we tend to see toxins occurring in late summer and early fall. And then overall, the detected toxins across Lake Champlain remain low in concentrations and in how many detections we're seeing. And they remain below, a lot of those critical drinking water standards, especially because we haven't seen them in the finished water. These figures here are just showing you the systems that have had detections and seasonally when those are occurring. So the state of Vermont has a pretty extensive cyanotoxin monitoring program that has in recent years expanded into the inland lake systems. And then what this figure is showing you is the percent of cyanobacteria reports collected from beach sites across Lake Champlain, which was put together by Peter Isles in the Watershed Management Division. So this is the beach monitoring program that is kind of held in tandem with the drinking water program. So in Lake Champlain, the sites that we see that are most at risk for high alert cyanobacteria blooms typically occur in the northern portion of Lake Champlain, which is much shallower and more nutrient rich than the main lake. So to break down what this figure is showing you, right, is the overall percent of reports. So there's a volunteer monitoring program where volunteers will go out weekly and they'll look at a specific beach site on the lake and they'll say, okay, it's generally safe, which is indicated in green. It's a low alert, meaning that there's some cyanobacteria, but not a full bloom, which is indicated in the yellow. And then the red is a high alert, meaning that there is high concentrations of cyanotoxins present. And then as you can see, the systems that have the highest concentrations of those high risk blooms are going to be in Missisquoi Bay and St. Albans Bay, which are in the northeast arm. And then when I refer to high alert blooms, what I mean essentially is that we're seeing these dense surface blooms that exist throughout the entire water column and extend for a pretty large aerial coverage. So they're not just a couple of cells that you see, it's a pretty large surface scum bloom. And then potentially even more important, we tend to see blooms become most toxic. We see microcystins being produced most frequently at the high level alerts, even though it is possible to have microcystins produced at blooms that are indicating generally safe conditions. So that's what this figure is showing you here. So this is taking the total number of toxin samples that were collected in this program and showing you when there were detections, where were they found, and the highest concentrations and the highest number of samples that test positive for microcystins were generally found under those high bloom alert situations. And then if you had a generally safe condition, you could still see cyanotoxins or microcystins present, although the levels were generally close to that detection limit of 0.3, and in some cases a little bit higher. So with that said, cyanotoxin production in Lake Champlain does remain relatively low, even during dense surface blooms. However, that doesn't mean it will always be the case and that we still need to display a sense of vigilance when monitoring blooms for cyanotoxin production. And cyanotoxin production can occur even when we don't see a huge surface bloom. That again. So pivoting to the upcoming season, There aren't going to be any significant changes to the practice than what was occurring last year, and we'll be operating under the same general protocol. So the only change that can be expected really is that we're going to have a slight change in the custom courier route. So we're going to be removing 2 pickup sites, but those were beach sample sites, not where you all were, dropping, leaving your samples at. So the only thing that might change is the overall time of when you had to have your sample collected by. And I'll show those schedules in a couple of slides down the line. The monitoring season is going to, again, last for 18 weeks, and it's going to start the week of July 7th, and we'll run through the week of November 4th for a total of 18 weeks. And then we're going to continue to sample only for microcystins again this year, because that's a toxin that's of primary concern in Lake Champlain. So for your reference, I will also be sending out the cyanobacteria monitoring practice for you all in an email after this. So you can read it and, understand the total thorough protocol. And generally, the program is going to be run as follows. So participating water systems will sample raw water and finished water weekly from July 7th and, as I said before, November 4th. And then following sample collection, samples will be dropped off at your designated courier drop-off locations on Mondays or Tuesdays. And following sample collection, raw water samples will be analyzed on Wednesdays. The process will be started on Wednesdays, and results should be sent to us, hopefully by Fridays, but potentially on Mondays. If your raw water sample ends up testing positive for microcystins, Vail, which is analyzing the samples, will automatically test your finished water sample, and then we will contact the water system and request that they take a confirmation sample as soon as possible. If the finished water sample exceeds 0.3 micrograms per liter, or if that confirmation sample exceeds 0.3 micrograms per liter of microcystins, then we're going to ask the water system will issue a do not drink notice. And then if the water sample exceeds 0.3 micrograms per liter and the finished water is below detection limits, I will request additional information from you all so I can calculate the estimated concentration of finished water microcystins. And then based off of those results, the sampling frequency may change to daily if the concentrations are expected to exceed 0.15 micrograms per liter, and the finished water twice per week if those concentrations might be between 0.3 and 0.15 micrograms per liter, and then it will remain weekly if the concentrations are expected to be below 0.03 micrograms per liter. And this is all detailed very thoroughly out in that monitoring practice too. And then again, just like last year, we will be packing up and distributing kits for all of you, which I think those have been distributed or they're in the process of being distributed right now. So in each kit that you've received, there will be a total of 19 bags for 18 total sample events, plus an extra bag of supplies in case you need one for a confirmation sample or if something happens. And then if you run out and need more sample vials, just reach out to us and we will contact Dale and figure that out. Each sampling bag is going to have 2 60 milliliter glass amber vials, one which will contain sodium thiosulfate, which is a quenching reagent for the chlorine in the finished water. So the bottle that has this label is going to be for your finished water, which is going to be post-chlorination. And then the other bottle is going to be for your raw water sample, and that again is before any treatment. So there's also going to be a field sheet and a separate plastic bag, which is different from last year. So we put this field sheet in a small sandwich bag, and we're going to need you to fill this out every time you do a sampling event, and then fold it back up and put it right back in that bag, because last year there were some complaints from Vail where the field sheets were getting wet and they would have to lose them out to dry, or they couldn't read what was on them. So we had to communicate between you all and with Vail to get that figured out. And then there's also going to be 2 bottle labels, which will look like this again, which will be placed on each of these amber vials and filled out with a single Sharpie. So when collecting your water samples, be sure to identify which bottle again is going to be used for which sample. Oh, are we having issues with the
We do. Two individuals saying they can't see the presentation. I see it fine on my end.
Did
I
I
think
can stop and try to share it again?
I think we can see it, Kate. So I think it's a matter of Mitchell and Jason maybe leaving and coming back on to see if that might help.
Okay, I think they just re-entered. So I'm wondering if that was like an issue because they left and came back if they can't see, but I don't know.
Is anybody else having that issue other than Mitchell and Jason?
All right.
Mitchell's in, yeah.
Okay, well, I'll carry on, and if they still can't see it when they come back, I'll try to like unshare and reshare that screen. Hopefully it'll get back up.
Yeah.
Okay. So when collecting your water samples, be sure to identify again which of those bottles are going to be used for which sample. So the sodium thiosulfate is going to be used for your finished water, and the bottle that doesn't have the quenching agent is just for your raw water. You'll then uncap your bottle and then fill it up to the shoulder, which is indicated here on this fill line. And then replace the cap, and then you're going to dry the bottle off so it doesn't get wet. And then you'll write on those stickers your information, so the time, what sample it is, your WSID, and so on. And then after you fill the bottle up, you can place that sticker on the dry bottle. And then you'll repeat that process for the second sample, and then fill out your sample field sheet again and place it in that Ziploc bag. And then you can place all of your completed samples, so both of those bottles and the field sheet, back into the larger Ziploc bag that it came in, and then put it on ice in the cooler, and then take it to your designated courier pickup location. And then when filling out the field sheet, please do fill out all components of our field sheets, because if these are not filled out, we will be getting phone calls from Vail or emails from Vail, and then we're going to be calling you, and it's going to be some, back and forth to try to figure out those times, because they can't accept a sample unless all this information is present in there. So again, what that's going to look like is you're going to write down, you're going to specify whether it's your raw sample or your finished sample. You're going to put your collection date on and the time of your collection, who collected it, and then the WSID. And then if you have any like specific notes that you want to put on there, like I dropped a bottle cap just in case, something happened or something happened to the sample when you were taking it, just so we have that type of information in case anything might come back a little weird. And then same thing for the field sheet. You're going to write your water system's name, the WSID, and then we also are asking you to circle if there is a current bloom going on outside of your water system. So you can say either yes or no for that. And then repeat that same information that you put on these sticker labels onto this section here. So these lines should match with the corresponding data that you wrote down on your sample bottles. And then this section over here up in gray is simply for the lab's use, so you don't have to fill anything out. And then again, just a reminder to please fold up your field sheet and put it back in that separate Ziploc bag so it doesn't get wet and damaged. For our sample drop-offs, please be sure to drop off your samples at least 30 minutes prior to the scheduled pickup time listed below. That's going to help us ensure that the sample is not missed by the courier in case there are subtle changes in the overall route schedules. And then for the Lake Champlain systems, you will collect your samples and have them set out or dropped off at the same locations you used last year on Tuesdays. And then in the lake systems, please have your samples dropped off at the closest health office or state health office on Mondays. If for some reason you are unable to collect a sample on that given week, please do let us know so we can relay that information back to the courier so they can pick that designated pickup spot. All right. And I'm just going to show what those courier schedules look like. So feel free to snag a picture of this. I'm going to also send this schedule out to you all individually after this meeting is over. So for the inland lake systems, you're still going to follow the same procedures that you followed last year with where those pickups are going to be. Just make sure that you get those samples in there before this time because this is when the courier will be coming in. Give it a second, yeah, for the pictures. And then for the Lake Champlain drop-offs, this is going to be the schedule this year. So the times are just slightly different than they were last year. I have a question. All right, so the times are going to be slightly different than they were last year. And if you have like an address change or something, let me know. But this is for the same systems that participated and are participating this year. Again, make sure, please, to drop your samples off at least 30 minutes before your designated pickup time. That way we make sure your sample is there and we don't have the courier missing it. And I'll leave this space for a picture, but again, I will send these out to you. All right. So following the sample submissions on your Monday or Tuesdays, depending on whether you're an inland lake or a Lake Champlain system, Vail will most likely report those cyanotoxin results to us on the Friday or Monday following the samples, the sampling events. So if your samples have detections, the drinking water and groundwater division, or we will notify the water systems, we'll call you and email you all directly when those results come in. Otherwise, results will be emailed to the water system contacts and uploaded to our websites by Monday following the test results. So the link to access where those are going to be can be found here. And then I'm also, again, going to send up a follow-up email with all this information for the links and everything after this training event. All right. So that leads us to our first break, but this might also be like, let me see, it's 2:40. Maybe if anyone has like any large outstanding questions about that protocol, we can take a couple now and then take a 10-minute break.
That sounds like a good idea.
So yeah, if anyone has any questions, feel free to ask us. If not, we can meet back at 2:50. All right. Let's meet back at 2:50 then. All right. Welcome back. We have a lot of cameras off, so maybe if we're back, I can get like a thumbs up from the folks in the room. Couple of thumbs up. Maybe even just push that like little, there we go. Some of those bottom ones, thanks, the emojis. So this next session is going to be focusing on how we can expect cyanobacteria blooms. Is the hands up a question or is the thumbs up from Warren?
Kate, I don't know, Tim, do you need anything in addition for credits?
I seem to have people pretty well trained. They're signing back in after each break, and I didn't even ask. So thank you for that. I think I'm good.
Oh,
Perfect.
great, perfect.
Oh yeah, I see all the names coming in. Look at that. All right. So this next session is going to be focusing on how we can expect cyanobacteria blooms and water quality to change under climate change. And I'm also going to show you all some data from some local inland lakes in Vermont and then some data from Lake Champlain as well. Get this. So climate change is expected to threaten the quality of surface water globally, primarily by altering the thermal structures and chemical interactions within water systems. The unpredictable nature of extreme climatic events, including things like extreme droughts or storms and flooding, can create long-lasting impacts on surface water characteristics. Under climate change, the frequency and intensity of these extreme climatic events are expected to increase. And with these events, we can see substantial patterns in delivery and concentrations of dissolved substances like micropollutants and pathogens changing. Wow, here comes a thunderstorm. Speaking of extreme climatic events, all of which water systems are going to have to navigate when treating water for distribution. I'm going to close my window really quick before it starts downpouring. All right, so with increased air temperature and solar irradiation, it's going to be expected that water temperatures are going to increase in the water. And that's because you have more light heating the water. And such increases in this temperature can drive changes in chemical reactions. They can cause reductions in dissolved oxygen at depth and cause shifts in the biological communities that can alter overall lake functioning. So you can see species shifts and nutrient changes and all of these things that can cascade into larger changes in your surface waters. And then with increased solar irradiance, we can expect potential changes in the characteristics of natural organic matter because the UV can, degrade it or change what you're seeing. And that can impact the formation of DBPs, which is something that I know a lot of us on, surface waters are concerned about. But for most of this talk, I'm really going to hone in on the idea of these extreme weather events and these changes in thermal structures as a result of increased water temperatures and how cyanobacteria blooms might respond to those stressors. Can you all see? Okay, now I was like, there was a pop-up on my screen and I didn't know if you could see that or not. It went away. So before I can really talk about how climate change is going to impact blooms and what that might mean for cyanotoxin production, I'm first going to discuss with you thermal structures in lakes. And I'm sure as we are all on surface waters, we're pretty well aware of, some of the implications of stratification and what happens, but I'm going to dive in a little bit here. So how climate change is going to impact, cyanobacteria blooms is going to be largely dependent on the geomorphology and nutrient regimes of a given water source. And when I say geomorphology, I mean things like the overall depth of the water and the shape of your lake and what nutrient concentrations you have. So if we take a deeper, lower nutrient lake, for example, we can say it's something representative of like Lake Champlain's main lake. Or maybe say the Waterbury Reservoir in Vermont. these lakes are going to be very deep and can exceed like 25 to even 100 meters in depth, or say 75 to 300 feet deep. In deep lakes, what typically happens in the summer is that the sunlight will come in and it will penetrate the surface of the lake and rapidly deplete at depth. And we'll see differentiations in the heating of the different layers of the lake, where you can have really warm water at the surface, colder water right at the middle, and then coldest water at depth, which causes a change in density between these three layers. And with this difference in density, you're not going to have mixing occurring between these layers. So you have three distinct sections of the lake. And then when you have rapid loss of light at depth and colder water that's not mixing with the top, you're not going to have photosynthesis happening because light can't penetrate. And then there's going to be a lot of biological activity that's going to eat up all that oxygen. And in the presence or lack thereof, in the lack thereof oxygen, what you're going to have is this mechanism called internal nutrient loading, where phosphorus and nitrogen are going to pulse out of the sediment. Because in the presence of oxygen, iron and phosphorus are going to be bound together. And when oxygen is no longer there, they both dissolve and that phosphorus becomes bioavailable for biological activity to use. And if we think about climate change, we can see that with increased warming waters, you can have longer periods of stratification or more intense stratification. And what can happen in cases like this is that with increased stratification and increased duration of stratification, you can actually potentially see a loss in productivity over the summer. So a potential for an actual decrease in cyanobacteria blooms. And that's if your lake gets its sources from internal loading. And that's because that lake isn't mixing and they don't have access to those nutrients that are locked in at depth. However, if we consider a shallow lake, say a high nutrient eutrophic system, that might be really shallow, like 9 feet or 18 feet deep maximum. Say an example of this could be Missisquoi Bay or St. Albans Bay in the northeast arm of Lake Champlain. Then you're going to see a different thermal structure happening. Because typically these systems are what we're going to call polymictic, which means that they have a fully mixed water column that's an even temperature multiple times throughout the year. So it's very rare that they will set up a strong stratification pattern that you'll see in deep lakes. However, in shallow lakes, light can typically penetrate to the bottom of the water column, which can cause this rapid heating of the entire water column. And wind is going to easily stir up and mix the entire water column to make it a relatively uniform temperature from top to bottom. However, even a slight amount of stratification can cause rapid loss of oxygen at the sediment water interface. So even if you have just like a touch of water that gets a lot colder at the bottom, you're going to have a lot of microbial activity that's going to eat up all the oxygen, and you can still have pulses of nutrients coming from the sediment. However, during a hot summer stable day, where you might have little wind, it's a great boating activity, we're outside recreating, these shallow water systems can have temporary stratification develop, where that surface water gets really warm relative to the bottom water. And then you can have that differentiation between the two layers with rapid depletion of oxygen at depth. And this rapid depletion of oxygen over a greater volume of the bottom water is going to cause a huge pulse of nutrients into the system. And if we think about climate change, with increased hot, stable days potentially in our summer, we can see that the strength and duration of this stratification may temporarily increase in shallow systems, leading to really large increases in nutrients that can be available for the phytoplankton and cyanobacteria to use to grow. So we really care about this, as I said and briefly mentioned in the last slide, is because internal nutrient loading in shallow lake systems is going to be the primary driver of cyanobacteria blooms in this type of system and is expected to worsen with climate change. So for instance, again, just to review this, if we have a heat wave that comes around and it increases the water temperature in the surface water, and you have thermal stratification developing where our surface waters are much warmer than the bottom, and then we have a subsequent loss of oxygen at depth, we're also going to see that internal nutrient loading of both nitrogen and phosphorus. And then during these events that deliver nutrients to the system, you're going to see incredible cyanobacterial biomass growth, potentially leading to these large, nasty surface scums that look something like this, which is a picture from last summer following a really warm, stable period in Missisquoi Bay. And when we consider how climate change is impacting this thermal structure of lakes, we can see that globally, surface waters are getting a lot warmer over time. So what you're seeing here is just some figures I pulled out from a couple of research papers that have looked at how lakes are changing across the globe, not just regionally here. And what we can see, or I guess what I have found most particularly alarming, is that for our region, the Northeast temperate region, that has lakes that experience ice cover, we're seeing that these lakes are warming at rates that are 2 times faster than air temperatures alone. So our lakes are getting really warm, especially our smaller lakes. We're also seeing that globally lakes are experiencing earlier onset of that stratification pattern that I described in the last couple of slides. And we're seeing that the stratification is breaking up later. I am not putting those up right. So what this means is if we have earlier stratification setting up and it's lasting longer into the season, it's that our waters are warming a lot earlier in the spring. So we've been having a lot of really hot, warm summer, like early spring days, and that's causing stratification to set up in some of these lakes. And our falls are also getting a lot warmer. And if we have the stratification set up and lasting for a much longer amount of time, that's going to facilitate a longer period of nutrient loading that could potentially fuel algal productivity, particularly in shallow lakes, and could potentially cause an inverse reaction in some of our deep lakes. And then to bring this pattern a little bit closer to home, I'm going to show you some data here about some remote inland lakes across the state. So in 2022, I was working with the DEC in the Watershed Management Division on a Sentinel Lakes project, which is essentially a project that deploys these high frequency temperature sensors on 5 remote lakes across the state in order to understand how climate change is influencing lakes that are minimally disturbed by anthropogenic factors. So we can isolate the factors that might disturb lakes and just look at like some of these changes in climate to assess what's happening in these systems. And I have data for 3 of those lakes over a 3 to 4 period of time. And what we can see is that in these lakes, we've had decreasing duration of ice cover across the lakes in the winter periods over this short period of time. And then we've also seen an increase across these systems in the length of that stratification period. So what they're finding globally is also what we are finding here regionally. And I also want to pinpoint that this is only 3 to 4 years of data. So this could just be a small trend that we're seeing over a couple of years versus say something that's necessarily happening over like 10 to 20 years. But the goal of this project is to try to assess what's happening in these lakes global over this longer period of time. So in general, why should we care about this changing thermal structures in lakes and the warming waters? I'll change my slide to tell you why we should care. So as someone who has studied cyanobacteria previously, spent a lot of time researching blooms, I think that the threat of climate change is of particular concern, and that's because it's anticipated that climate change in combination with eutrophication or the addition of nutrients into our watersheds is going to create a catalyst for toxic cyanobacteria blooms. And that's because cyanobacteria have a really high temperature optima, which means that they can grow really quickly and really efficiently at higher temperatures. Say, I think the classic number that you see like in the literature is 24 to 25 degrees Celsius. And I don't know exactly what that translates over into Fahrenheit. So at these temperature ranges, they can outcompete other algae and grow into these thick surface scums. If we have increased and prolonged durations of stratification, we can see enhanced cyanobacteria growth because cyanobacteria can alter their positions in the water columns via those gas vesicles that I showed you in the first slide. So when it's really sunny and hot, cyanobacteria can sit at the surface of the water column by expanding those gas vesicles, and they could collapse them and sink to the bottom of the lake or to the thermocline, that middle region where nutrients are actively available, and they can move up and down to use those nutrients and then go to the light and grow. So climate change may actually make Climate change may cause decreases in the duration of ice cover in lakes, which can cause increased light penetration into the water columns in the winter months. And because cyanobacteria have adapted to a wide range of environmental conditions, they can grow actively in the colder temperatures in the winter, potentially accumulating into cold water blooms. So there's been evidence and increasing evidence being recorded that you can have under ice blooms in lakes. Or this scenario can also cause a strong seed population that can lead to stronger blooms that could happen over the summer, potentially increasing bloom severity. So not only are we seeing that blooms can, be impacted this way under climate change, we're also seeing that cyanotoxin or toxin strains can increase in abundance with increased temperatures as well. So what that means is that under climate change, we might not only see more cyanobacteria, but we might actually see more toxic cyanobacteria, particularly toxic species that can thrive under warmer water temperatures. So just to bring this back locally, I don't want to bog people down by this figure, but I just want to mention it and show it. So we're seeing that locally, heat waves and warm waters can trigger increases in cyanobacteria biomass, particularly in shallow eutrophic systems of Lake Champlain. So this figure is a figure from my dissertation research, showing some of the work that I did over the past couple of years. And I don't want to spend too much time here, but I do want you to pay attention to this solid black line across 2018 and 2021 in Missisquoi Bay. And what that represents is essentially the relative percent of cyanobacteria in the water column at a given time. So this is from high frequency data that's collecting data every 10 minutes across the entire season. And what we can see is that during heat waves, which I have indicated here in these red boxes, that oftentimes we can see cyanobacteria biomass increases during that duration of this heat wave. And the bars, these red arrows here, are indicating the heat waves where this pattern has occurred. So parsing out some of this data and some of these responses can be a little bit challenging because shallow lakes are highly respondent to changes in weather patterns. But what we know is true for Missisquoi Bay is that these stable warm periods facilitate large pulses of nutrients from the sediment, which then fuel cyanobacteria blooms and allow them to grow. And again, I just kind of want to highlight why we really care about this. And that's because in Lake Champlain systems, we see that the most toxin concentrations are typically associated with these high level, high alert blooms. And when blooms are increasing in severity, our drinking water is going to be most at risk for cyanotoxin exposure. So that also leads us to our next section. So we're pretty quick on time here. So I'm also happy to take any questions here. If not, then we can have another quick break and move on to our next section. Yeah, Ray?
Thanks, Kate. I wanted to reiterate a few things that Kate just said. And, I think that she's put into graphs and words and facts what we're really all feeling about what's going on with the lake right now. It's not only just that the temperature is going down, but the precipitation events are increasing. And when we get all this together, when we see more precipitation, higher temperatures and all of that, it's not just cyanobacteria that we have to worry about. It's basically all of the kinds of things that we're dealing with now. I know a lot of you have recently had issues with disinfection byproducts, and all of this is coming at us. And I'm just really afraid that it's with us permanently. We might want to try and dismiss whatever quality deteriorations that we've seen in the lake as kind of a fluke or something that, okay, it happened 2023. I'm afraid that that's not the case. And it's just going to make your job and our job a little bit harder, and just something to be aware of. When Kate presented this to Silly and me the other day, so we could look at it, and I'm just looking at the graphs and seeing these numbers and saying, yeah, this is what we've been seeing, but it's all kind of been anecdotal from my standpoint. And now we're just facing the hard facts.
Thanks, Ray. That's a good point. And I think like just a point to touch on too, maybe, is this whole idea of these extreme climatic events and how we can have this increase in the frequency and intensity of a lot of our storm events. And then that could sometimes be followed by these drought events. And if we think about what that means for cyanobacteria and the blooms in the lake, is that if this pattern keeps occurring, you can have huge deliveries of nutrients into the system. And then you could have this stable hot period a couple of days later. And that's just gonna, again, create this catalyst for these blooms to really just take off and grow. And it's something that I think we need to be aware of, and something that we need to plan for potentially, what happens if these become toxic. Like right now, blooms aren't very toxic in Lake Champlain, and that's good. But yeah, planning measures for just, what could happen is going to be important.
Yeah, I
Well-
mean, go ahead, Silly.
Well, then I want to chime in as well, because one of the things that I found really interesting with Kate's presentation, and that was new to me, was this idea of how, certain strains will produce toxins while others won't produce toxins, and that the influx of nutrients can change the overall type of strains we are seeing in Lake Champlain. And so right now, we may not have a lot of those that are microcystis that are developing the toxin microcystin. But if we keep having, the influx of nutrients, and with climate change, that type of strain may change. So it's that to me was also a very interesting piece of information, that, just something to think about. And especially in, bringing it up to the higher level of source protection, and how you as operators of water systems, you're advocates for source protection. And how do we talk about it in a broader term, source protection of how do we prevent nutrients from entering into our surface water bodies, so that we don't have this change in the strains that will then produce more toxins. I think that is, also a very interesting conversation when thinking about cyanotoxins, but that it actually has like this broader implication on source protection in general. Sorry, Ray, you were going to say something as well.
Oh, no. For a long time, I'd have to admit, I was kind of a skeptic on the whole cyanotoxin program. And the reason was simply because we just were never seeing positive numbers, or numbers that were so infrequent that I just kind of just came on the decide that this is nothing to worry about. But it takes an expert like Kate really to convince me that really I'm really was on the wrong track. And I say that simply because of these dramatic changes we're seeing in the lake. And so, frankly, even though we're not seeing it now, I almost see the handwriting on the wall on Lake Champlain, the way things are going, is that we are going to get into a much more difficult position. And I say Lake Champlain, it's probably true of all the other lakes as well, just because of the increased precipitation and the increased temperature. So, the way I think about it is like, if you look at the Great Lakes, the poster child of cyanotoxin is Lake Erie. And when you talk to the folks who are operating treatment plants in Lake Erie, you realize how far we will need to go in order to get up to speed if and when those conditions happen, or anything close to those conditions And yet, if you're on like a Lake Superior, you're much more like we are at this point, and not really worrying about it. So anyway, just another thing to put on all of your plates, unfortunately.
Don't have any questions about blooms and cyanobacteria and the climate change aspect, or just any mechanisms for anything. I'm happy to take any questions. We're a little bit ahead of schedule here, so um, we have some time. If not, we can meet back in 10 minutes.
Yeah, let's do that, Kate. And just before everyone drops off for a 10-minute break, just want to put it out there that the next session Kate is gonna take us through is developing emergency response plans. And this is going to be a short section in terms of presenting, and then more an interactive session with you all to talk about what are you doing for considering what to do in the situation of microcystin in finished water. So just a little prep for you to come back and be ready to participate in a conversation, because this is really not something we are luckily we haven't been needing to deal with up until now, and hopefully we won't this summer either. But it's better to be prepared, and so starting the conversation around what happens, who do we contact, what do we message, all of those things. We'd love to hear from you, your thoughts on that process when we're back.
All right, you want to do 3:20? We can do 3:30. The 13-minute break. Come back at 3:30.
That sounds great.
Excellent.
Hey, Jason, can you hear me? It's Carol.
Yeah, I can hear you.
Yeah, Tim Russo asked about dropping off water sample kits tomorrow, and I
Yeah, if
told
you want to leave them at your place, that's fine.
okay,
And then you send them up with Travis.
okie doke. Sounds like a plan. Did you hear that, Tim?
Yes, thank you both.
Yeah. Yeah, I'm actually taking tomorrow off, so it'd be more convenient for me anyway.
Yep. Okie dokie. We got a plan.
All right. So I guess as folks come back, if they want to do that sign on again, like you had done the last section that Tim has suggested, that'd be great. Great. Okay. So as Scylla mentioned, this next section is really going to be more of a discussion amongst all of us. I have a couple of slides that I'll start with. And then we really want to be able to learn from you all and how you all are implementing some of these, because we aren't, we're not experts in developing these response plans or running them. So I always, okay. So given the context of how climate change can impact cyanobacteria blooms, it's going to become increasingly important for water systems to develop emergency response plans to prepare for scenarios where cyanotoxins may persist in finished water above that 0.3 micrograms per liter threshold. Hopefully we aren't there yet, but it's going to be much better to be prepared than to be caught off guard. So in order to do that, we should discuss what emergency response plans are. So emergency response plans can help water systems explore vulnerabilities, make improvements to, and establish procedures to follow during emergencies. Emergency response plans can describe your water system strategies, resources, plans, and procedures to prepare for and respond to different incidents. And in this case, we're talking specifically about high concentrations that may have broken through your finished water and are sustained there. When developing emergency response plans, there are several steps that are going to need to be taken in case of an emergency. So one of the first ones is going to be creating a chain of command for emergencies. So once you have a water sample that has detected microsystems that are greater than 0.3 micrograms per liter, while we're waiting for our confirmation samples, who will carry out the emergency response plan and the ongoing decisions that are going to follow? Creating a list of contacts who can be responsible for specific parts of this plan will ensure efficient decision making, and it helps create accountability in the face of emergency. Next, we're going to need to create a robust plan for communication, and this is going to include knowing which internal and external parties that are going to need to be made aware of the different types of communications. In the case of a finished water detection that exceeds 0.3 micrograms per liter, you'll need to issue a do not drink public notice within 24 hours of the confirmation sample. So for templates and protocols for this do not drink notice, you can see the cyanotoxin monitoring protocol, which I will be sending out following this meeting. Other questions to consider include which staff members are going to be designated to reach out to your vulnerable communities, who will be responsible for talking with the local media sources, and what will you say if you get questioned. Similarly, if continued concentrations of microsystems persist in your finished water samples, do you have a plan for how you will adjust treatment? Again, our cyanotoxin monitoring program practice, I think, outlines some of those adjustments. And then lastly, if needed, do you have any plans for system shutdown and where you will source alternative water options from the cyanotoxins if they cannot be, do you have alternative plans for your water source if you have persisting cyanotoxins in your water and they can't be properly treated? I don't know if we want to take a minute here, Ray, if you want to talk about some of that treatment side of things. If not, we can hold off on the end because we have an hour before 4:30. So.
Well, of course I can talk about it, but
maybe minusculely quickly.
it'd probably be better to hold off. We can discuss some of the communication issues first. Right. But I can talk a little bit about the whole treatment end of things if everybody is going to be deadly silent.
All right, we'll hold that for the end when we have our questions. All right. So the EPA has several different resources for creating management and response plans, particularly for cyanobacteria blooms, some of which I'll be happy to send out for folks following this meeting. I briefly wanted to share this protocol here with you all, which was designed by the EPA in 2016 for creating a cyanotoxin management and response plan in public water systems. So this plan is essentially broken into several different steps, which start with assessing your water system's risks and vulnerabilities to cyanotoxin exposure. So thinking about historical patterns, what the nutrient loads look like in these systems, when are blooms going to occur, and how are you going to prepare for potential early warning bloom monitoring signals. And then it helps outline monitoring plans, again, for these early warning signs of cyanobacteria blooms, helps outline plans for raw and finished water sampling protocols, and can help you lay out and plan for communications if microsystems are detected at any point in your raw or finished water samples. But in 2015, the Drinking Water and Groundwater Protection Division worked with several TNCs that sourced water from Lake Champlain to create management and response plans, understanding that many community systems likely have had other plans in place prior. So these existed in 2015. And if your water system is interested in seeing those or revisiting those plans, then we'll be more than happy to send those to you for your reference. So we have some on Lake Champlain that do exist, and they follow a really similar protocol to this. So following a similar structure to that plan, the Drinking Water and Groundwater Protection Division has developed cyanotoxin monitoring program to help assess water system risk to cyanotoxin exposure by conducting weekly sampling during the bloom season and to help identify best treatment options for cyanotoxins and drinking water. However, we would love to learn from you all. So what are you all planning to do if continued exposure to cyanotoxins does occur in your drinking water? And with that in mind, this next section is really going to be focused on some questions that we would encourage you all to consider when developing these emergency response plans. So we encourage any water system here who has a plan or a system in place to share your experiences with us and your answers to some of the questions that we have outlined in our next slide. And we really encourage you all to help turn this into a discussion where we can learn from each other. So some of those questions are, I think I'm just going to read this off and then I can take a moment to answer questions or to have us facilitate a discussion. So some of those questions that we should consider when developing these emergency response plans include things like, what protocols do you have in place if there are detections in the finished water? So if you have 0.3 micrograms per liter detected, what are your next steps? Who are we contacting? What are we doing? Who are your vulnerable populations in your sourced area, and how do you reach those vulnerable populations? Do they have any emergency plan in place for this type of detection? And what will you do if you purchase water from a contaminated system? Who will you need to communicate with? Again, internal, external partners, the public. Will you need an alternative water source if you have continued toxins in your water? And then how long will it take to implement your response plan? Are all staff trained and up to date on emergency response procedures? How are you going to respond to journalists? And how and when will you return to normal operating conditions once a bloom has passed and there are no more toxins in your water? And then along with that, do you have a flushing plan to return to normal operation? So that was a lot of questions. Does anyone have, any water system here present have an answer to any of these, or have you worked on emergency response plans for cyanobacteria blooms before? Do a thumbs up if we have thought about the emergency response plans, if we're being shy. Go ahead, Scylla.
Yeah, so so as Kate was saying, a number of TNCs worked with, I believe there was Vermont Rural Water Association to develop emergency response plans. And I guess I see a name in the chat. I don't see which system you are with, and I apologize for not knowing that. But I'm just curious. I know that Apple Island, Bow and Arrow, Burton Island, Kemps Island, Paradise Bay, Ruthcliffe, Sandbar State Park, and Thompson's Point had these plans developed. Anyone from any of these systems that are on this training that know where those plans are, have looked at them since they were developed in 2015, would be able to pull them out and go through it in case of an emergency? Are there no one from any of those systems on here today?
Have to look through, but I don't see anybody.
Okay. What about, okay, so then let's think about it in a different way. So there are at least 9 systems in the cyanotoxin monitoring program that are required by EPA. It was enacted in 2018 that any system with over 3,300 people served need to establish an emergency preparedness plan and notify EPA that they have it. Are there any of these systems on the call today that would speak a little bit to those plans and what goes into those plans? Are they answering some of these questions? What were your process in developing these plans?
Well, there certainly are some people from these water systems, and by their silence, I'm guessing that they don't know anything about these plans, or they don't want to speak about them. I'm not sure which, but somebody out there, Mitchell. I see Virgins Panton is on there, and you just started at Virgins Panton, so it may be that you know nothing about this. Confirm or deny.
Hey,
Is
Sela,
he
is my
still there?
microphone still too low?
We can hear you.
We can hear
Okay,
you.
so for everybody
Oh, Tim.
that's being quiet right now, I believe we're talking about the American Water Infrastructure Act, and I personally assisted a number of systems on the risk and resilience assessments, and even did one ERP. I don't have the bandwidth to do ERPs again, but that's on a 5-year cycle, so I'll be coming around again, and if you don't hear from me, hit me up and we'll update the risk and resilience assessment. Oh, and
That's correct. Yeah,
yeah,
Tim.
and Sela, as you were talking about the specifically the cyanotoxin ERPs, those were developed by our former ED Sean Fielder all those years ago. I can't speak to their relevance now or even then because I didn't review them, but I might be able to still get my hands on copies if anybody's interested.
We have them, and so if any of the systems that any of the TNCs would like them, we can also send them around. It was more just, are people aware of them? Have they read them recently? Are they still applicable? We can see that some of the information is outdated, just with the emergency contact numbers and names. And I guess we're just trying to have, we're no experts, and this is more just where are we at with this? Is this even on anyone's radar? How would you respond if, let's say, Virgin's Panton end up having a cyanotoxin microcystin above 0.3 micrograms per liter in the finished water? Do they know where to find the do not drink public notice? Do they know when to issue it? Do they know who to contact? And if not, how can we help you better understand those things?
So this is Tom Garofano with the City of Rutland. We do have our emergency response plans. Looking through these questions that you have here, it seems to me, now we don't have a cyanobacteria response plan, but it looks like it could be easily incorporated into our do not drink orders if we have an E. coli hit. Just the only difference would be that we would probably be contacting you and Ray and figuring out how to go about our flushing procedure, which I'm assuming would be very similar to if we had a E. coli hit in our system. It doesn't appear like there would be much difference from our emergency response plan. If it was in our primary reservoir, we could switch to our emergency source after we communicated with water supply. That would be my only question, trying to merge the two together, as with concerns to being in our filter beds and how to handle that. If it's in our finished water.
I don't know if we want to get off track on the emergency response plan at this point, but certainly what Tom said at the end is very important in terms of responding to a raw water detection. Because what you want to make happen is if you have it in your raw water, you want to do everything in your power, given the types of treatment that you currently have, to minimize the transfer of the cyanotoxin from raw to finished. So I'm prepared to speak about that, but I don't want to interrupt the conversation about the communication and the emergency response, and that's in that vein yet.
Yeah, thank you, Tom, for chiming in. I'm curious. I'm curious about. I think that there's a lot of elements from your emergency plan that you can apply to the cyanobacteria and cyanotoxin issue. I'm curious about. I think this came up in a conversation with Megan Moyer once from Burlington. That they have, UVM hospital on as part of their system, and that there might be a lot of vulnerable users there. And I'm curious about, do you have any special users on your system that would need to be notified before or in a special manner to make sure that they get what they need in this kind of an emergency?
Yeah, yes, as we do with any public notice we've sent out for any disinfectant byproduct violations, we have a email list that is email, phone calls to the hospital, to nursing homes, to any critical care facilities and schools. So we're in communication with those facilities constantly, especially seeing that we've had disinfectant byproduct violations in the past. So there's been quite a bit of communication and an open line for many years now.
Okay, well, that's, not great. I don't want to say that's great, but in a sense, a good experience to have, because that is directly, relatable and applicable to this situation here. And I know, Tom, you were so kind to chime in, so now you're sort of the target for all of my questions, and feel free to bounce it to someone else or say, I'm going to pass on this one. What about something like responding to a journalist? Because obviously a cyanotoxin exceedance will be something picked up by, the media. Is that something that anyone has thought about and know how to respond to, etc.?
From my experience, of course, I've only been chief operator a couple of years here. It seems as though I want to get the correct answer from the people that know more about this issue than I do. I would be deferring to you for the right answer, and either bouncing it back to you guys to speak to the press, or public works directors, the mayor. I think when the operators get involved with that, it takes away from the task at hand, dealing with the issue. That's my personal feeling.
Mm-hmm.
That should be more at administrative end for state officials and department heads, not the operators, again, dealing with the issues.
Mm-hmm. I heard Bridget from the health department actually say in her introduction that that was something the health department could help with, the health language and response. Any thoughts from you, Bridget?
No, I mean, that's absolutely true. This, the press has picked up even detections in the past in the raw water. They like to follow the websites and see that information. So, just trying to get the right information out there. I agree, like as operators, you're trying to address the situation, make sure it's not worse. And I think that's the message that you would kind of put out. But like, working with us, we're always happy to provide that that language so that the accurate language is getting out there for press releases and that kind of thing, or wording for Front Porch Forum. EPA has a toolkit out there for cyanotoxins in drinking water, like a whole risk communication toolkit there. It's a little the way they approach it is a little more complicated than we do because they have two different levels. They have a level for a more vulnerable population, which is lower, and a level for adults, which is higher. We kind of don't think that level of nuance is appropriate for the risk communication because it's so really complicated. So that's not the approach we would take, but we can still take some of that language and kind of build on that to relay the information that we would like to. And yeah, health department's always happy to help. Oftentimes that would be like in concert with DEC. So, if you're alerting DC or DC knows information first, they'll loop us in and then we can work together to make sure the information that we're putting out is accurate.
Thank you, Bridget. Maybe just a thumbs up or raise of hands. How many have seen the cyanotoxin the practice and is aware of the do not drink notice and the treatment protocol in that practice? Thank you, Jason. All right. Okay, so I think just for everyone's awareness, thank you, Jason, for knowing about that in the practice. I just to put it out here so that people, because this training is also just an awareness. I don't think any of us expect you to memorize these things. It's a matter of having a conversation around what is available, where can you find the resources, and who do you reach out to. But basically, in the cyanotoxin practice, we update every year if there is a need to update it. That practice describes the process for the monitoring program. And then in the appendix, we'll have the do not drink notice that you need to use in case of an emergency. And then the next appendix is basically how to tweak your treatment if there is a detection. So just be aware that if this happens, then those resources are available in that document. And of course, if you can't find that document, reach out to us and we'll help you find that document, but also, of course, help you, give you the language, help you deal with the treatment tweaks. But just recognize that information is living in that document.
Yeah. And I'll be sending that out also in a link following this training event.
Well, I am, we can keep asking questions. I think maybe the question now is, would anyone be interested in hearing about the treatment tweaks that Ray can talk about, or do we want to, has this created, food for thought? And are there any questions or any thoughts or any considerations associated with these emergency plans that you're sitting with and would love to share?
This is Austin with Simon Operations Services over at North Hero. I know that sodium permanganate is a treatment option for some of the cyanotoxins, but we're primarily using it for muscle control. And we were looking at controlling some of our DBPs earlier because we had a bit of an issue. But we were increasing the dosage, and what we noticed that when we were increasing the dosage, our turbidities were going up on our filters. We were actually having a flock breakthrough. So just wanted to make you aware that sodium permanganate is also a bit of a coagulant aid. So you might want to adjust your dosages when you do that.
Austin, I can elaborate a little bit more on the permanganate issue, and especially as it relates to cyanobacteria and cyanotoxin. If you want to think about this issue, think about it in two ways. The first is the toxin that's contained within the cell. That's what we call intracellular microcystin, if you will. And then if the cell breaks apart, the cyanobacteria cell breaks apart, then the toxin is no longer contained by the cell wall and it's free to move through your filter. And this would be any type of filter you have. So if you think about it that way, the first thing you want to do is contain that cell inside your filter and not let it get through. So that relates directly to your filtration. You want to optimize your filtration as best you can to make sure that that as little as this toxin is outside of the cell. So you bring up the permanganate that you're using for zebra mussels. That can actually have a detrimental effect on you're trying to get rid of cyanotoxin, because in addition to controlling zebra mussels, it can do this thing called lyse the cells, which is basically breaking the cells apart. And so one thing that we might want you to do, depending on how much you've got in your raw water, is to discontinue, at least temporarily, a treatment like sodium permanganate, which is going to hurt you in terms of controlling cyanotoxin. It's good for a lot of things, but it may very well be that it's something that you might want to discontinue if you notice that you've got raw water cyanotoxin. And then speaking of which, in terms of your filtration step for optimizing it, you're going to be doing all the things that you normally do, and then some. For example, in the case of Alberg, which we've had recurring cyanotoxin in raw water, one of the things that we carefully looked for when we spoke with Jason on this is making sure that the filters are not running too long. Because if you think about what happens in a filter, the cyanobacteria is concentrating in that filter. And so you may have X amount in your raw water, and if most of it or a large majority of it is contained in the cell, picture what's going on in your filter. Your filter is concentrating in the cells cyanotoxin. And you've got to be really careful about not running your filter too long and having something happen where the cells that are contained in the filter begin to break apart. And once they break apart in the filter, there is nothing to stop the toxin from going into your finished water. And so that's something that we need to be really careful about. Now, Tom, you mentioned that issue in your system, which is a slow sand filter. And that is something that actually I haven't really thought about. I mean, for a rapid sand filter, it's pretty easy to give advice. The advice is, you know what, if you've got a lot of cyanobacteria coming into your plant and it's being contained in the filter, you want to make sure that it's not going to break apart for the filter. Backwash those filters more frequently. Okay, don't allow the cyanobacteria to build up in the filter. And so if you're backwashing every 12 hours or every 16 hours, maybe we're going to come up with advice and saying, you know, instead of 16 hours, back that off to 12. So that's one thing about rapid sand. With slow sand, where your filters will run for months and months and months at a time, it's a little bit more problematic because it's hard to take those filters out of service at a moment's notice, wash them out, and put them back in service. That's a days or weeks, or sometimes in some slow sand filters, even a month-long process. So not really sure what we're going to do in the case of a slow sand, but it's certainly something that we need to keep in mind. Now, all that being said, the other thing we have to do is we do have to worry about extracellular toxin that's not within the cell. And I think Kate has mentioned this to me before in saying, or somebody has, maybe it wasn't Kate, but she's the expert I depend on now, is that if you get a really big bloom, usually what happens is you get the most cyanotoxin when that bloom starts to die, because that's when it all kind of breaks apart and dumps itself into the water. And once that happens, your filters are basically useless. They are not going to do anything for those tiny little molecules. I mean, even the best normal rapid or slow sand filtration plant is not going to remove stuff at the molecular level when it comes to a substance called microcystin. So at that point, we are dependent totally at this point on either adsorption using a granular activated carbon or adsorption using a powdered activated carbon, which will adsorb the toxin onto them. And then barring that, if we don't have that or if that's not working for us, then we have to rely on your chlorination. Fortunately for all of us, chlorine is a very effective method of inactivating or breaking apart or altering the chemical structure of a microcystin molecule. And so we have a table that we go to, and Kate mentioned this table before when she said she brought together where it showed how long you have to, how many, if you do get a raw water hit, how frequently do you have to take follow-up samples? And you notice it depends. It depends on how much inactivation of cyanotoxin we think you're going to get. And that's all strictly a mathematical formulaic thing that we're using. All we're doing is we're plugging in your chlorine residual and your CT, your pH, and your temperature. Just the thing that you do normally every day, because we require you to do CT. We're going to use that in a different formula, a formula where CT and those other factors are plugged in to see what, so that we can see how much in activation of cyanotoxin we think you're going to get. And if we think, your level coming in is really, really small, and you have a very good chlorine residual with a lot of detention time, and the pH is not too high, you're probably going to be okay just with what you're doing. However, if your a lot of systems, surface water systems, actually don't have that much CT, and we may be asking you to raise your chlorine residual temporarily, because really that's the main tool that we've got for you at this point. Other than if you're a Grand Isle Consolidated Water District, which has a granular activated carbon filter, or you're a Burlington or a Champlain Water District, or a Bellows Falls maybe, where all three of those systems in one way or another can activate a powder activated carbon system. We may be looking for you to get that system going, just because we don't want to leave any tool on the table if you start getting cyanotoxin in your raw water. For the main reason is that over 0.3 parts per billion with a confirmed sample, not just one, but a second sample, is going to bring you in what I call the water treatment plant death penalty. It's something we all want to avoid. And that is, boil water, we can live with that. But the do not drink order is the worst circumstance that we can imagine from all our standpoints. And so I've just kind of touched on a little bit on what I'm looking forward for you if you do get a raw water detection. I do encourage you to get the practice. I think it was over 10 years ago that I wrote the treatment guidance on that. And I gotta read it over again myself, because at this point I'm probably mentally diminished. But we'll see.
Ray,
Anyway,
I just added the practice link to the practice in the chat.
okay, that's perfect. So I don't want to belabor it, but just to give you a feel for what we're going to be thinking about and looking from you if you get the raw water detection.
Any other thoughts or questions? And the floor is open. It doesn't have to be about emergency response planning. It can be about anything about the upcoming season. the data we provided, treatment, all of the above.
I think it's just too hot out there today. Everyone is soporific. I'm in my attic, and we got that hellacious thunderstorm that Kate talked about, and now we're just, I think everybody can leave, and if you're near a lake, I urge you to go swimming.
I think that sounds like a good strategy. Yeah.
But yeah,
Yeah,
so
and I did go swimming yesterday, and I'm happy to report, and it's probably way too early. I saw absolutely no cyanobacteria.
how's the pollen in like the brown
There is
algae?
there is a huge amount of pollen.
Yeah,
It
yeah.
is like pollen everywhere.
Like aggregating up in the shorelines, and people keep thinking it's a bloom, and we're like, no, 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 it's just pollen.
Yeah,
Go swim if you want.
yeah.
Hey, Ray, it's Kevin Knapp. I think in years past, we've talked about lowering the pH also as a potential effective measure. And just thinking about that a little bit, we don't have much control over the pH coming in. And it seems like that would probably be the one you'd want to affect, or you want to do it post filtration.
Yeah, and you bring up a good point, Kevin, and that is that for chlorine to be effective, it wants the pH to be lower because chlorine exists in two forms, and it's all dependent on pH. It exists in the free, what they call the hypochlorous acid form, and that predominates at low pH, and the hypochlorite ion form, and that predominates at higher pH. And just like Giardia or other bacteria, the microcystin molecule is attacked by the free chlorine much more effectively than by the I don't mean free chlorine, but by the hypochlorous acid and not by the hypochlorite ion. So, but we have to be careful on that, of course, because you're raising your pH to control lead and copper. And so, if things are desperate, I think maybe we will want to go to a little bit lower pH, but I'm certainly not going to bring you out of the effective range. Like for example, for you, Kevin, you use orthophosphate. You use combination of orthophosphate and pH to control lead and copper. And so, the literature says 7.2 to 7.8. I wouldn't want to fall outside that range. So if you're running at, 7.5 or even 7.4, maybe you could go down a little bit, but certainly below 7.2, I'm not going to recommend.
Yeah, I think we're actually allowed to go down as low as a 7 up here. Other places, yes, it is like a 7.4 is our low spot. So really system dependent, obviously.
Yeah. Yeah. There's a lot of nuances in the treatment. And so, other than Alberg, where we've had the drill many times at this point, if you're going to have a confirmed raw water detection, you can expect at least one of the three of us, and maybe all three of us, to descend upon you. Because, that's how we learn how to control these things. So, it's really helpful to us that you are in this program. Because if systems did not volunteer for it, we could never gain an expertise that would allow us to understand how to control the treatment and what to do specifically to avoid a finished water detection. So, it is a little bit scary to be in the program because it's voluntary. And so, therefore, you could take the attitude, I don't want any bad news. I don't want any trouble. I don't want anybody around me. I'm not going to, ignorance is bliss. But in this case, from a public health standpoint, what you're doing, giving us the opportunity to see what's going on in your system and monitoring it, and being the guinea pigs really is really helpful to us. And so, it's invaluable to us that you are volunteering in this program.
And I'll see if I could find it. I'm not sure. I wasn't able to while Ray was talking, but last year Chase gave a presentation about the this tox tool that we use to sort of identify the breakdown of microcystin based on pH and contact time. And there are some slides there about how pH and contact time affect the treatment of microcystin. And if I find it, I can pass it on to Kate, and Kate can share that as well if anyone's interested in the slides from last year's presentation, which was a little bit more geared towards the treatment side of things.
Anyone have any final last questions? If not, we can grab a couple 10 minutes back. All right. You guys can expect to hear from me. Like, I'm going to send out a follow-up email with the cyanotoxin protocol, the practice, and a couple other bits of information regarding what the season is going to look like, as well as a copy of this recording. So if folks couldn't see it who wanted to be here, they can have a version of it to watch. But other than that, thank you all for coming, and very excited to be able to work with you guys this summer, and I'm excited to be here. So here's to a low bloom summer. We can hope.
Here, here. Thank you.
Thanks,
All right,
everybody.
bye, everyone. Thanks.
Bye.
Thank you.
Maybe Jeff has something he wants to say because he's lingering on.
Perhaps. I'm gonna stop the recording.
That's why I came back on to stop it.
Yeah, I guess I can. Well, it would stop automatically once.
Trying to
but,
figure out how to get out of here.
You can stay.
Bye.